Hi everyone. So today I'm going to introduce our work on parallelizing Monte Carlo tree search. The title is Watch the Unobserved, a simple approach to parallelizing Monte Carlo tree search. This is a joint work with Jianshu Chen from Tencent AI Lab and Mingze Yu, Yu Zhai, Xuewen Zhou, and Ji Liu from Seattle AI Lab, Kwai Inc. MCTS algorithms have achieved great success in solving many challenging artificial intelligence benchmarks such as computer Go, chess, and video games. It is one of the core methods in model-based reinforcement learning. Below, we can see some example applications, such as the Go AI AlphaGo and the Chess AI Deep Blue. So let's introduce some background on Monte Carlo tree search. In general, we are interested in solving MDP-related problems using Monte Carlo tree search, or MCTS for short. Intuitively, an MDP describes the process of interacting with an environment at discrete time steps and get a reward signal. At time step t, the agent will observe state st from the environment. After it takes an action at, the environment will transit the next state st plus 1 and also emits a reward rt. This process repeats until some termination conditions are met. The agent's goal is to perform a sequence of actions that hopefully maximizes the cumulative future reward. Here, we are interested in using MCTS as the policy to take action. Let's take a closer look at MCTS. The power of MCTS comes mainly from the ability to foresee different future scenarios with the environment model. This is generally referred to as planning. MCTS uses the information gathered by performing simulations on the environment model to build a search tree, which can be seen as an incomplete game tree. We then use this information to decide the highest rewarded action. The MCTS algorithm recursively performs throwout, which consists of 4 steps. First, in the selection step, the algorithm recursively selects child node until it arrives at a leaf node or some other terminal conditions are met. Next, in the expansion step, the algorithm selects an action to expand and construct a child node accordingly. After that, starting from the state related to the newly constructed node, MCTS performs simulation using a default policy pi. And finally, after simulation completes, MCTS updates the visited node with a simulation return. The 4 steps are repeated to gradually build the search tree to approximate the value of each node to find the highest rewarding action for the root state. We demonstrate how to decide which child node to select in the selection phase. First, note that there are 2 statistics in each node of the search tree, that is V and N. V refers to the empirical average long-term reward of the node, while N is the visit count of that node. We use a policy called the tree policy to decide which child node to select. Intuitively, it constructs a score for each child node and picks the node with the highest score. The score consists of 2 parts, V, the exploration term, and an exploration term built from the visit counts N. These 2 terms naturally forms a trade-off between exploration and exploitation. There are 2 important things to note. First, in the selection step, we use the statistics V and N to make the best exploration-exploitation trade-off in node selection. That means we are using all past information which comes from the simulation to select the best node. Another thing to note is that the backpropagation step can only happen after the simulation completes, as it has to update the cumulative reward returned by simulation. So why does MCTS need parallelization? First, empirical results have shown that given an MCTS algorithm, the more the samples, the better the performance. This means we need many samples to satisfy certain performance requirements. However, the sampling process requires extensive interaction with the environment, which suggests that sampling is time-consuming. Together with the above takeaway, we know that MCTS is computationally heavy. Practically, most current successful applications adopt extensively parallelized MCTS. So what are the fundamental challenges of parallelization? Ideally, when there is an oracle that gives us the simulation outcomes as soon as simulation starts, the full set of past statistics are available. This means that at time step t, we have t different simulation results that are embedded in the v's and n's of the node. This is equivalent to the sequential case. Therefore, we have the same amount of information at the selection step comparing to the sequential case, and hence we enjoy zero performance loss with respect to the sequential algorithm. But this is impractical as we don't have the oracle. Practically, since when a worker performs simulation, the outcomes of ongoing simulations in other workers are obscured, so we tend to experience high performance loss. But why in practice the performance loss will be high? So we illustrate this by two classes of potential failure cases. The first is called collapse of exploration. If multiple workers simulate the same node, then the algorithm is less efficient in terms of exploration. However, if we force different workers to simulate different states, the efficiency of exploitation will be sacrificed. That is, even if we know some nodes are preferable, we still tend to explore anyway. So we want to find some balance between and to avoid both failure cases. The first thing we should try is to add more information to the statistics. However, the simulation results are not available until simulation returns, so we cannot really improve upon it. For N, it is already ideal with respect to its definition, and we also cannot improve further. Our approach, which is unobserved in UCT, is based on the following observation. Although not being able to anticipate the simulation outcomes before they actually terminate, we are aware of its existence as soon as it has been initialized. Therefore, we can incorporate this information to build more powerful parallel algorithms. Practically, in addition to V and N, we introduce O that counts the number of simulations that has been initialized but not yet completed. And correspondingly, we adjust the tree policy used to select child nodes at the selection step. So a natural question to ask is why WUUCT can work. Conceptually, WUUCT pre-shrinks the upper confidence bound. This gives two potential benefits. First, it incentivizes exploration by shrinking the upper confidence bound for visited nodes. allowing the algorithm to efficiently explore less visited nodes. Additionally, it can also maintain exploitation, since when n is large here, adding O in the second term have little effect on the value of the upper confidence bound. We built a system to implement the above idea. Due to time limit, I will not go into details, and interested reader can refer to our paper. We perform experiments to justify the effectiveness of WUCT. Here we show two examples. First is the results on Atari games. The bar refers to the average and standard deviation of WUCT's performance with respect to different number of workers. The line refers to time consumption per step. First, look at the red line. You can see that WUCT achieves near linear speedup. Then, from the bar plot, we can see that there is relatively small performance loss when the number of workers increase. Here, performance loss is with respect to the performance of the sequential algorithm, which is when there are only one simulation worker. WUCT also has superior performance comparing to existing methods. WUCT has been successfully adopted by the industry. We have leveraged it to build a system to predict the average user pass rate in various levels of a mobile game called Joy City. With this significantly ease the level designing process. So at the left side, we show WUCT's performance on two typical levels of the game. We can see that we enjoy linear speedup as the number of workers grow. Also, while being more and more parallelized, WUCT has consistent performance. This allows us to trust the algorithm and take advantage of the speedup it provides. At the right side, the user pass rate prediction system then uses the AI's performance and the human player's performance to build a model that can predict the user pass rate in new levels. If you are interested in this part, please refer to our paper for details. For future work, we are interested in understanding why WUCT works from a theoretical perspective. We divide the cause of performance degradation in parallelized MCTS into two aspects. The performance degradation caused by the tree policy in the selection step, and the performance loss caused by the tree topological structure. We show that WUCT solves the first problem by satisfying its necessary conditions, while other existing approaches does not. This corroborates the superiority of our method. However, WUCT cannot solve the second problem as certain necessary conditions are not satisfied. This helps to guide future research directions to build even better parallel MCTS algorithms. Thank you for listening to the talk. Special thanks to all my amazing collaborators and also Yitao Liang and the Dongdong Group for helping me to prepare this talk. Thank Xiangru Lian for his help on the system implementation. Also, this project is open source, so if you are interested, please check out our GitHub repo, and thank you.